I'm sharing my screen. Yeah. So in the last class, we seen about what is a clock domain. Okay. So clock domain, that means here in the digital we already seen like single clock is there. No. So single clock, that is nothing but synchronous clock. Okay. That is nothing but that is synchronous. Okay. So multiple clocks are there means we already seen that. So single clock. So we already seen the synchronous counters and asynchronous counter. This is having the single clock. So this is nothing but single clock domain. Okay. So some designs, so practically what happens, most of the designs, different domain, different peripherals will be operated at different domain, different clocks. Okay, so there you need to work on different clocks. So that is nothing but clock domain crossing. Okay, that is nothing but CDC, clock domain crossing. Different clocks are there. Those are nothing but asynchronous. Okay, so that we discussed. What are this? So before this we discussed about asynchronous. Synchronous flip flop have a common clock is there. Okay, whereas asynchronous flip flop is there. So different clock will be there, and so for the you have separate write clock and read clock for the asynchronous FIFO. Okay, first in first out. Basically that is a not that is a queue. Okay, in order to avoid the data loss we are using this FIFO. Okay, so we already seen that is asynchronous. Asynchronous means suppose one clock is having the high frequency, other clock is having low frequency. Clock 1 is having the low frequency and clock 2 is having the high frequency. Then different designs are operated different clocks. Okay, you have write clock and read clock. Okay, those two clocks are independent to each other. Okay, that is nothing but clock domains. Okay, two clocks will operate independently. Okay, that we are saying that is nothing but we call as clock domain crossing, CDC. CDC is nothing but clock domain crossing. Okay, there are some CDC techniques also there. Okay, that we need to learn about the CDC techniques. Okay, and so I told you, so that means how we can do how we can learn means I told you like there are three methods are there in the asynchronous clock domains. Those are nothing but clock domain crossing techniques. One is using handshaking signals and using asynchronous FIFO, and next one is using flip flop synchronizers. Okay, so using handshaking signals not that much preferable, so we will use in the asynchronous FIFO we use flip flop synchronizer, and as well as you are using asynchronous FIFO. Okay, so like if you consider this one. Okay, so two clocks are there, so data will be transmitted from master. There is a master and slave. Okay, so before data is transmitting from master to slave, so slave should give the acknowledgement. That means I am ready to receive the data, then only the data will be transmitted from master to slave. Okay, this is nothing but handshaking. Okay, this is nothing but one type of handshaking. This handshaking we can see in the I2C as well as SPA also. Okay, those peripherals we can see you have like master and slave. Okay, so master wants to send the data from master to slave. First it will send the acknowledgement signal whether the slave is ready or not. Okay, whether the slave is ready or not, it will send the acknowledgement. After that, after getting the acknowledgement only, then it will send the data to the slave. Okay, so if acknowledgement is not coming to the master will understand that like so slave is not ready to receive the data. Okay, so that means like in I2C also you have like clock and data enable pin is there, so those are like synchronized with that. That is one type of serial communication. Okay, I2C and SPI also, serial peripheral interface. Okay, you have like single master, multi slave. Okay, single master and multi slave. So multi slave should be communicated with each other. Each and every slave has specific address like that. Okay, so that is nothing but what handshaking. Okay, so yesterday also I told you like two persons are there in that there is a wall. So the one person is throwing the box from one side to other side from the wall. So that means every time the other person should be like attentive. Okay, so there is some handshaking. Suppose they will talk with each other that within after 2 minutes he will send the data. Okay, so like that. So after every 2 minutes what happens, every 2 minutes he can means ready slave will be ready, so that master will send the this person will throw the box. Okay, that is nothing but understanding, or we can call as handshaking signals. Okay, that is nothing but handshaking. Okay, and next we are dealing with what, using asynchronous FIFO and flip flop synchronizers. Okay, so asynchronous FIFO so FIFO. So as I told you, why you are using FIFO means you take two modules are there. Okay, suppose this is one module, and another one is this is let us take sender and receiver. Okay, this is sender and this one is receiver. Okay, sender is operating at 50 megahertz and receiver is operating at 25 megahertz. So this is high, this is operated at high frequency and this is operated at low frequency. So that means when it is sender is sending the data directly, there will be loss of data. Okay, in order to overcome that loss, you are connecting a FIFO in between sender and receiver. Okay, you are connecting this one from sender and receiver. Okay, that is the main agenda of FIFO. Okay, synchronous FIFO also we discussed. Okay, so this is the main operation of FIFO. Okay, in order to avoid the data loss, okay, we are using this FIFO. Okay, so two clocks will be, so asynchronous means what, suppose synchronous FIFO means common clock will be there. Okay, this is common clock. Okay, common clock given to both sender and receiver. Okay, and this is asynchronous means what, different clocks will be there. Okay, different clocks will be there from the sender and receiver. Okay, so that's why we call as asynchronous FIFO. Okay, so different clocks will be there, and different clocks will be operated at different clock domain. Okay, so that is about asynchronous FIFO. And this diagram I took from VLSI Verify. So you have like what we call like FIFO. This is FIFO. Here you have write pointer and here you have read pointer, and so that means data in is how many bit? This is 8 bit. Okay, data out is also 8 bit. Okay, write enable. So write enable is 1 bit only. You have write clock and read clock. This is also 1 bit. Okay, and so here towards right pointer there is FIFO full. Okay, there is a FIFO full, and towards the read pointer there is FIFO empty. Okay, so last class we already seen the conditions also, when it is FIFO full and when it is FIFO empty. Okay, that also we need to see. Okay, and next here binary write pointer and binary read. For every read and write operation, this binary write pointer and read pointer will be incremented. Okay, like a counter. Okay, so like 0 0 0 0 0 1 0 1 0. Okay, and so why we are using gray code means, I told you there is a large difference. Suppose consider like 0 1 1 is there. Okay, next it will come to wait 4 bit means 1 0 0. There is a large difference, no? So large difference, that's why you need to go for which counter means a gray code counter. Okay, the gray code counter is one distance or one hot code. So the distance between two bits, let us take 0 0 0 1 1 1 and 1 0. Okay, so if you compare between two bits, there is only one difference. Okay, 1 bit difference. Okay, so that's why we are doing this gray code pointer that is given to the flip flop synchronizer. Okay, this is the gray code write pointer synchronizer, and you are giving to gray code a read pointer, and it is given to the flip flop synchronizer, and it is given to the gray code read pointer. Okay, so that is so again write so this is reset. Okay, actually this is nothing but we are giving to like clear signal. Okay, this is write reset and read reset. Okay, write reset and read reset underscore n. Okay, so as I told you, like in digital we are using what type of reset? Asynchronous active low reset. Okay, active low reset. Okay, why we are using also, that I told you. Okay, that means here during the power off it will be in which state? Reset state. Okay, and as I told you, like when it is going from reset mode to functional mode, that is synchronous with the clock, and when it is going from functional mode to reset mode, it is nothing but it is asynchronous. Irrespective of clock, it will reset. Okay, so why we need that asynchronous reset means sometimes my clock will not work. Okay, you want to reset your circuit. Okay, so you can't reset if it is synchronous. So that's why reset applied is what we call asynchronous. Okay, reset removal is synchronous only. When it is functional mode, reset removal is functional, that is synchronous only, but reset applied, whenever the reset applied is there, that is asynchronous. So that we discussed with related to the D flip flop. Okay, so again, what is the main advantage is directly it is connected to the clear signal. So there is timing path is not required. Okay, timing, no need to calculate the timing path for this. Okay, suppose if it is synchronous reset, if I am using synchronous reset, so suppose this is a D flip flop, and here there is a mux, there is a 2 cross 1 mux connected to D, and if it is active low reset means this is here you need to give reset underscore n, and this is given to 0. Okay, 0 is given to D input, and if it is 1, okay, if it is 1, D input is given. I need to calculate the timing path for this also, no? Okay, so timing path also, timing path for this 2 cross 1 mux also I need to calculate the timing path. Okay, so this is one of the disadvantage. That's why we are not using synchronous reset. We are using asynchronous reset, that to active low reset. Suppose if it is active high reset, okay, if it is active high reset, so when it is going from where to where, functional mode is 0, reset mode is high. Okay, when it is reset mode is high, normally when the power is on, you are operating your design in the reset mode. Okay, so that is not required. No, you are applying extra power in the reset mode. Okay, in the reset mode, that is not required. When the power is off, your design should be in which mode? Reset mode. Okay, so that's why we are using active low reset, asynchronous active low reset. Okay, so that is about the reset. Directly if it is given to clear signals of these two right pointer handlers, and so as I told you, know, so like two flip flop synchronizers are there. Okay, this is for sender and this is for receiver. Okay, sender and receiver. Okay, and these are the signals you have, and yeah, sender will send the data to the receiver. Okay, so why we need this synchronizer means, suppose this is passage of clock. Suppose it is passage of clock. Okay, so in digital we already seen the ideal case. That means ideal case means what? During this passage of clock, what happens during this passage of clock? Whatever the data is there, you are getting. But practically, what happens means, so it should follow some setup time and hold time violations. Okay, so what is that setup time means? What setup time means? Input should come before this passage of clock. Input should come before this passage of clock. So this delay, okay, this delay, during this delay, input should be constant. Okay, this is nothing but we call as setup time. Okay, after that, input should be constant after rising edge of clock. Okay, so this is nothing but clock hold time. Okay, this is nothing but hold time. Okay, this is nothing but hold time. So it should follow some setup time and hold time. Okay, if it is not following, you are getting some violations. Okay, so when you are getting some that violations, it will go into metastability state. Okay, this is metastability state. Metastability state means whatever the receiver flip flop is there, it will not identify whether that means the sender is sending the signal, that will be not sampled into receiver signal. You are getting either 0 or 1. Okay, it will go into what? Metastability state. Metastability state. Okay, so here that means the main part of synchronizers is here. So here this is so flip flop 1. So the output will changing during this edge. So it is not following the setup time and hold time violations. It will go into this metastability. Okay, you are getting unknown. After that, what happens? It will go into stable state. Okay, after that it is going to the stable state. That stable state output is given to which flip flop? Flip flop 2. Okay, so after sending, that means here you are getting metastability. Okay, the output here you are getting what? Metastability. After metastability, the output becomes constant. This constant output is given to which flip flop? Next flip flop. Okay, so these are nothing but we call as flip flop synchronizers. Okay, we need to synchronize, or we need to make the output as stable to avoid the setup time and hold time violations. Okay, so flip flop synchronizers are there towards right pointer handler, and these synchronizers are there in read pointer handlers also. Okay, so two synchronizers will be available, okay, towards right pointer handler and read pointer handler. Okay, and so every time the data is written, here there is a right pointer will be incremented. Okay, and suppose data is reading by the read pointer, every time the data is reading, so what happens, the read pointer will be incremented. Okay, so when the FIFO is full, so full is when right pointer equal to read pointer. Okay, read pointer, that is, then we can say that FIFO is full. Okay, we already seen the condition full, that is nothing but right pointer equal to read pointer, then FIFO is what, full. Okay, so when FIFO is and this is FIFO is I think FIFO is full. Okay, so that is a condition we already seen in the last class. Okay, that is so metastability, I told you, no, it will go into unknown state. Okay, and why we are using this binary gray code pointer means I told you, like basically when it is doing right pointer operation, every time it will be incremented. If it is a 2-bit, it will be incremented from 0 0 0 1 1 0 1 1, and if it is a right pointer also 3-bit means it will be incremented like this. Okay, so you are using, for this you are using what, binary counter. Okay, for read pointer also, for every read operation it should increment for 0, so 0 0 to 1 1. Okay, so that means here so why we are using this gray code means, suppose when you are, suppose if you take 4-bit number, okay, that read pointer or right pointer is 4-bit. Okay, so here this is what, this is 1 1 1 1. When it is changing from, so normally first case if you see, there is only one change is there, only one change is there. Okay, 0 to 1 is there, remaining all are same only. But this case if you take, okay, this case there is a change in all 4 bits, there is a change in all 4 bits. Okay, so this many transitions are there. Okay, so that's why binary counter we will not recommend. Okay, normally the counter outputs are what, q3 q2 q1 q0, no, the flip flop outputs are only the counter outputs. Okay, so these transition, these 4 changes of transition we can't recommend. Okay, so that's why we are going for what, gray code. Okay, so gray code means what, gray code means there is only one change. Okay, suppose if you consider 0 0 0 1 1 1 and 1 0. Okay, there is only one change here. Okay, and if it is 3-bit, how to write, suppose 0 0 0 1 1 0 1 1 and 1 1 and 1 0. Okay, and here you write reverse, 0 0 0 1 1 1 and 1 0. Here you write 0, here you write 0, and here you write 1. Okay, so if you observe each and every bit, is differ by how many bit, only 1 bit only. Okay, so that's why you are using gray code counter, gray code counter. Okay, gray code counter. So that is the main thing, and so that is a gray code. Okay, gray code. Okay, so here why gray code? In the gray code only 1 bit change per increment, there is 1 bit change in the increment. Okay, that means if read domain samples during the transition, so 1 bit may be metastable and receives the older bit. Older bit is how much, suppose 0 1 0 0 is there, new values will be incremented, no, new value becomes what, 1 1 0 0. So if you compare 0 1 0 0 1 1 0 0, so these bits are differ by how many bit, 1 bit only, these bits are differ by 1 bit only. Okay, so this is the core reason why you are using a gray code counter. Okay, and we can tolerate the metastability on 1 bit. Okay, and even with gray code, this we can pass the gray code pointer to flip synchronizers also. That will means that will allow this gray code to the 2-bit synchronizers. Okay, okay, so that is about the 2-bit synchronizers. Okay, So I told you all those things. That means whatever the signals and full you are getting towards the sender side, and empty you are getting at the receiver side. Okay, and it is gray code is there, so you are converting this gray code. Okay, and inside before this, there is a FIFO write operation, and write operation is happening towards the right pointer, and read operation is happening in the read pointer. Okay, that I told you. Okay, write pointer handler and read pointer handler, and these all are the inputs and outputs we discussed. Okay, so full is occurred in the write pointer handler, and empty is occurred in the read pointer handler. Okay, so this is about the code, and next we'll go to the programming part. So if you see the programming part, I done the programming separately. So this is GVim. Okay, first what I need to do, so that means you have if you see this so you have two flip-flops, the two flip-flop synchronizers are there, no? So you need to write the program for these two flip-flop synchronizers. Okay, how we are writing? So if you see, one second, if you see this one, okay, so module synchronizer, so I am using parameter width equal to what, 3, and input clock reset, and width 1:0 D in, out reg width 1:0 D out. So what are the inputs for this flip-flop synchronizers? So that means there is a clock and there is a reset and a D input and D output. Okay, that input and output I initialized. Okay, and reg width, so in between these two registers, okay, these two registers, I am initializing one intermediate variable, that is q1. Okay, let us take this is q1 and this is nothing but q2. Okay, so here what I am doing, reg width down to 0, q1. Okay, always at the rate passage of clock begin if not of reset. Okay, passage of clock if not of reset. So q1 equal to what, q1 is initialized to 0 and d out is initialized to 0, and else begin q1 equal to what, d in. So else begin q1 equal to d in means what, whatever this input is there. Okay, one second. Okay, it is coming from the right pointer, no? So it is coming from the right pointer means you need to consider, one second, yeah. So this one is it is coming from the right pointer and clock is given. This is q, this is the intermediate is q1, and you are getting the signal from the right pointer, and this is q2, like this. Okay, this is q2. Okay, and so here you see, so q1 equal to what, d in. Okay, q1 equal to what you are getting, d in. Okay, q1 equal to, so d in you are getting. Okay, this input is getting, and q2 equal to what, q1. q2 equal to q1. So d out equal to what, q1. d out equal to q1, end and end module. So this is for what I wrote for flip-flop synchronizers. Okay, and I need to check whether the FIFO is full condition or empty condition. Okay, so there are two ways to check the flip-flop is full condition or empty condition. Okay, so one is what, one is this way one is you need to find out, that is when write pointer equal to read pointer, then we can say that flip-flop is full. Okay, and flip-flop is empty means what, so we need to use write pointer synchronizer equal to read pointer synchronizer, then that is nothing but flip-flop is empty. Okay, FIFO is empty. Okay, one more thing, so one more way is, suppose I will tell you this, so one more way here it is telling how it is doing means, I'll open this this one. Okay, suppose if you consider asynchronous FIFO. Okay, this is asynchronous FIFO. I told you, like, basically you are using gray code, no? So means in the number system or in the codes we already seen how to convert gray to binary to gray. How to convert binary to gray? Suppose if you take binary value, what is that binary value? 1 so that means let us take one binary value. Okay, what is that binary value means? Okay, what is that binary value means? 1 0 1 1. This is my binary value. Okay, so this is my binary value. How to convert? So this bit you take as it is and you do the XOR operation. You do the XOR operation. So what you are getting, 1 XOR 0 is 1, and 0 XOR 1 is 1, and 1 XOR 1 is 0. Okay, this is actual my gray code. Okay, this is actual my gray code. Okay, so this is what method 1. Okay, so method 2 means here how it is calculating means, first you take the binary value. What is that binary value? 1011. Okay, and this value shift left by one position. Shift left by one position. So when you shift left, what you will get? This one will come here, and this one will come here, and this one will come here, and whatever the vacant position is there, that will be loaded with 0. Okay, and you need to do the XOR operation with the original binary. So what is my original binary? 1011. Okay, so when you do 1011 here, this you are doing XOR operation. Okay, this you are doing XOR operation. So that means 1 XOR 0 XOR 1 is how much? 1 second. Here what you got in the binary? 1 XOR. Okay. 1011. Okay. And here what you are getting? 1 1 1. Okay. Here you need to get. Okay. So like this you are doing. You are shifting this one with the 1-bit position. Okay. Suppose you take binary value. Let us take 1010 is there. Okay, 1010. First this binary value is there, no? You shifted by one position. So what you are getting? 0 1 0 0. Okay, and you are doing the XOR operation with so you are doing the XOR operation each and every bit with my original number. Okay, my original number. So what is my original number? Original binary number 1010, no? So what you will get? 0 1 1 1. Like this you are getting. Okay, this is my gray code. Okay, this is my gray code. So like that I am calculating this this one. Okay, so see here. So that's like that I am calculating the binary gray code. Okay, so where I am calculating means here top module. This is top module, no? Somewhere I calculated this gray code sequence. Okay, yeah, like that I am calculating the gray code sequence. Okay, and next so this is method 2 and method 1. Way 2 I told you, no? So way 2, so how we are means how we are finding out this one means, so see here, suppose so you are calculating that FIFO full or not. So basically if it is 1 second. Yeah, see here, so normal FIFO if you take, okay, normal FIFO, suppose normal FIFO or synchronous FIFO you take. So when you that means here so you did when the FIFO is full, when read pointer, that is equal to write pointer plus 1 tick binary 1, then we can say that FIFO is full. Okay, when the FIFO is empty, so when the FIFO is empty, that is write pointer equal to read pointer, then we can say that FIFO is empty. These are nothing but what? There we considered binary pointers. Those are nothing but what? Binary pointers. Okay, so here we are dealing with what? Gray pointers. Okay, so gray pointers. So what are those gray pointers? So we converted the binary to gray by using method 2. So gray pointer, if you consider the gray pointer, so what you are doing? Empty, how we are checking? Gray underscore write underscore pointer, that is equal to gray underscore read underscore pointer. Okay, so that means here so how you are making as full means, by using this formula. Full that is equal to, that means right full equal to, how we are doing means that is equal to gray right pointer, gray white next, that is equal to not of gray pointer synchronous. Okay, and here you have pointer width is to pointer width minus 1, pointer width minus 1. Okay, suppose width equal to, let us take 3 down to 0. 3 down to 0 means what? That is 3 is to 2. Okay, 3 is to 2 comma gray read pointer synchronous. Okay, pointer, I am using parameter, that's why pointer width 2 down to 0. So 2 down to 0 means what? This is width minus 2. Okay, this is width minus 2. So this is 1 is to 0. 1 is to 0. Okay, so this condition I am checking. Okay, so I'll try to explain with one example. Suppose let us take okay, yeah, so you take suppose you take the gray value. Okay, you take the gray value here itself. If you see, you can understand this command. Okay, so see here, so that means let us take the gray value. Let us take the gray value. Let us take 15. Okay, 15. So that means this is gray of 15. Okay, gray of 15. Basically, this is binary value. Okay, how to convert into gray? I told you, like so basic method you follow. So that means this is 1 1 1. So each and every bit you need to do the XOR operation, and this bit you need to write as it is, and 1 XOR 1 is 0, and 1 XOR 1 is 0, and 1 XOR 1 is 0. Okay, so this is nothing but my gray code. Okay, so this is what 3 2 1 0. Okay, 3 2 1 0. Okay, so that means not of 3 is to 2. So that means gray pointer synchronize pointer width 3 is to 2 means what? Third bit. So let us take the gray pointer. Suppose let us take the gray pointer. Gray pointer is 0. 0 means what? 0 0 0 0. Okay, so this is what? This is 0 1 2 3. Okay, so I need to complement 3 to 2 bit. So I need to complement these 2 bits. So that is nothing but what? 1 1 1 1, and so gray pointer 3. So width minus 1. So gray pointer width and width minus 1. That means these 2 bits complement. Complement means what? I need to complement, and gray pointer synchronize pointer width minus 2. Width minus 2 means what? 1 comma 0. So 1 comma 0, this index 1 comma 0 you write as it is. Okay, if both are equal, then FIFO is full. Both are not equal, FIFO is not full. Here you see, so here gray pointer, gray right next, this is nothing but gray right next. Gray right next, both are not equal. Both are not equal means what? FIFO is not full. Okay, FIFO is not full. So like this we can say, like suppose these are the gray values, and if you see, these are the gray values, different values of gray to binary values. Okay, I will take one more example. Suppose if you consider gray right pointer is I am taking gray right pointer is 1100, where so during 9 you are getting, no, this value I will take 9. Okay, 9 means not 9. Okay, sorry, 8 I will take, 8 gray 1100. Okay, this one, not this one, this one I will take. Okay, so when I take this, okay, so when I take this, I will check this. Okay, so my gray right pointer equal to what? 1100, and gray read pointer, let us take 0 0 0 0. Same value I am taking. Okay, that is 0. Okay, gray 0, binary 0, both are 0, no? So first what I need to do, so this is the index. What is my index? 0 1 2 3. These both I need to complement. Okay, this is nothing but 1 1, and remaining 1 0 same as it is I need to write. Okay, so here these both are equal. These both are equal. Okay, so from this I can say that gray right pointer equal to these both are equal. Okay, that condition is satisfying. Okay, so what is that condition? This so FIFO full is nothing but gray right pointer next equal to what? Not of gray pointer synchronous pointer width is to width minus 1. Okay, 3 is to 2, and gray right pointer synchronous pointer width minus 2 is to 0. Okay, if both are equal, then FIFO is full. So here you got gray right pointer value is 1 1 0 0, and after calculating this you are getting 1 1 0 0. Okay, in this case FIFO is full. Okay, so if you observe this one, okay, so means within this after completing half of that values, the FIFO is making as full. Okay, so this is how you need to calculate either FIFO is full or not. Okay, so this is the full condition as I told you. So that means W fill equal to what? Gray right pointer next, that is equal to what? Not of right pointer synchronized pointer width is to pointer width minus 1. Okay, and gray pointer I am using concatenation operator. Okay, I am combining these two. Okay, so that means gray read pointer width minus 2 is to 0. Okay, so this is 3 is to 2. This is not nothing but 1 is to 0. Okay, I need to combine. Okay, and empty means that is empty equal to what? Same thing. So gray right pointer synchronous equal to what? Gray read pointer next, then we can say that FIFO is empty. Okay, and so this is about checking the FIFO is empty or full. And next I need to write the separately for right pointer and read pointer. Okay, so for right pointer handler, so pointer width I am taking as 3. So what are the inputs? Right clock, right reset underscore n, and right enable. Okay, and input. So input pointer width is to 0. So read pointer synchronous. Okay, and outputs are nothing but pointer width is to 0, right pointer, and so binary right pointer and gray white pointer. If you see here, if you see this diagram, okay, what are the inputs for read pointer? Okay, that I need to see. Okay, data in, right enable, right clock, and you have binary right pointer, gray right pointer synchronized. Okay, synchronous. Okay, all these inputs and right reset and w reset underscore n. These are the inputs I am giving to right pointer handler. Okay, so here you see, so right pointer handler. Okay, and register wraparound wire right full. Okay, assign right pointer next equal to right pointer plus enable or not of full. If it is not of full, then I can write the data into the right pointer next. Okay, and after that I told you, no, you need to convert binary to gray. So how you are converting? You are converting shifting by, I think shifting by right position plus XOR operation. So if you do the shifting by right position, 1 second, I will get or not. Okay, so see here, I told you, no, I told with shift with left, no. Suppose same method, if I do shift with right, 1 second. So this is my binary, no. Okay, I will rub this. Okay, I'll rub this. I'll check whether my gray code method 2 is following or not. Suppose first this binary method is there, no. Shift by right position means what? 1 0 1, and whatever the vacant position. So that means shift by, this is shift by right position by 1, and adding to the binary value. So that normal value 1 1. Yeah, it's satisfying. Okay, not left shift. I told wrong. That is right shift. Okay. So here you see. So XOR operation. So here this is 0 1 1 1. Okay. Both are same, no? Method 1 and method 2. So method 1 I did normal method, whatever we discussed in the digital normal method, converting binary to gray code. Okay. So this gray code I got. Okay, this gray code I got. Okay, this gray code I got, this gray code and this gray code, both are same. Okay, so first binary value you need to shift to right and add with the original binary value. So this is how you are converting binary to gray. Okay, binary to gray. Okay, it's not left shift, it's a right shift. Okay, so see here, so same thing, assign gray white pointer next equal to what, binary right pointer next shifted by one position, and XOR operation with binary right pointer next. Okay, this is nothing but what, this I can say that, so this one I can say that, binary to gray conversion. Okay, conversion. Okay, and at the rate, always at the rate passage of clock and negate of reset. Okay, so in the sensitivity list I need to give with asynchronous active low reset. Okay, these are the sensitivity list. Okay, passage of right clock and negate of right reset begin if not of reset. So what you need to do, so default values, so base right pointer you need to initialize to 0 and gray white pointer you need to initialize to 0. Okay, and else begin. Okay, else begin you need to increment, no? So for right operation you need to increment the binary right pointer. So binary right pointer equal to what, binary right pointer next. Okay, and gray right pointer equal to what, gray right pointer next. Okay, and next I am checking for whether full or not. Okay, so this is nothing but checking whether so full or not is nothing but I am checking towards which pointer, right pointer. See here, full I am checking towards right pointer. Okay, so here you see, so that means second, yes, so always at the rate passage of right clock and negate of right reset begin if not of right reset full equal to what, 0. Okay, full equal, no full, so no full, else that means full equal to right full. Okay, I am checking for this full. Okay, and assign, how I am assigning, that means right full equal to, I told you, know, so that method. Okay, so that this method where right full method, I told you, know, where I told here I told right full. Okay, so like this, that means binary, so I am converting into gray, and this one I am complementing, and I am checking whether these both are equal or not. Okay, so that is nothing but full condition. Okay, so this is nothing but so gray code right pointer next equal to what, not of read pointer synchronous, pointer width is to pointer width -1, gray code read pointer synchronous with pointer width -2 is to 0. Okay, so this is about the right handler. Okay, this is the code I wrote for right handler. Okay, and so this is for right handler, asynchronous FIFO Verilog code for right handler. Okay, and similarly read handler. So read handler means what are the input for read handler? You have binary read pointer, gray code read pointer, and gray code read pointer synchronized, and read reset underscore end, and empty will come in the read pointer. Okay, and if you see, so module read pointer handler parameter, how many bits, pointer width is 3, and I am considering the inputs as what, read clock, read reset, read enable. Okay, read enable also there. When read enable equal to 1 only, then it will do the enable operation. See here, data out, read enable, and our read clock also there. Different clocks. Right clock is for write operation and read clock is for read operation. Okay, read enable also there. Okay, those inputs I am initializing, and input pointer width is to 0. That is gray code write pointer synchronize, and so 4-bit. 3 down to 0 means what? It equal to 3. No, this is 4-bit, and output reg pointer width is to 0. Okay, this is also 4-bit. Base read pointer and gray read pointer, and output reg empty. I need to check for the empty, no. So this also I am initializing as a output. Okay, empty. Okay, and next initial begin, right clock equal to 1 tick binary 0, and right reset equal to 1 tick binary 0, and 1 second, this is TB, sorry. See this is nothing but so reg I am initializing base read pointer next, and gray read pointer next. After reading operation, that right pointer and read pointer will be incremented, no. So that I am initializing with next, this is the reg values. Okay, assign base read pointer next equal to what, base read pointer plus read enable and not of empty. Okay, not of empty, then it will do the read operation. Okay, so this is nothing but binary to gray code conversion. Okay, here also I need to convert binary to gray code conversion. Okay, so this is also binary to gray code conversion. Okay, gray code conversion. And how you find the empty? That means gray code write pointer synchronize equal to gray code read pointer synchronous, then FIFO is said to be empty. Okay, and I need to do the read operation and write read operation, no? So that means always at the passage of clock or negate of reset begin, if not of read reset begin. Okay, so base pointer read base read pointer and gray read pointer I am initializing to 0. So that is nothing but reset if not of reset end. Okay, else begin base read pointer equal to what? Base read pointer next. After reading operation the pointer will come to the next thing, no? That's why. And for similarly gray read pointer I am equal to non-blocking operator gray read pointer next. Okay, and so and always at the passage of clock and negate of reset, if not of reset empty equal to 1, else empty equal to empty. So I am checking for empty whether the FIFO is empty or not. Okay, here I am checking for empty or not. Okay, and FIFO memory full also I told. Okay, FIFO memory full. Okay, and so here you need to write separate programs for all this what we call first I wrote for the flip-flop synchronizer, and then I wrote for the right handler, and I wrote for the read handler. Okay, in the top module what you need to do, you need to call this header files. Okay, include synchronizer.v, include write pointer.v, tick include read handler.v, and include read memory. This is nothing but reading your memory. Okay, reading your memory. Okay, and you need to initialize the inputs, and you need to initialize these parameters. Okay, and you need to initialize the synchronizer. Okay, synchronizer, all those things you need to initialize. Okay, so this is about the program related to asynchronous FIFO.